Welcome back, everybody. Yesterday we covered some speed, talked a little bit about how that works. Today we're going to be going on to position and displacement. So we're starting to move into vector territory. Haven't had to deal with them yet. Don't worry, we're going to get lots of practice. So remember, a vector is something with magnitude and direction. So it's going to matter which way things are going to be moving. We need to know where something is. That's the only real difference between it and distance, which is its scalar equivalent. So hopefully you guys had some good success when it came to working through your various practice problems. The answers are online. You can take a look at them, as are the answers to all of this part. You can find all of that in the teacher booklet in the same folder as the student booklet. But let's take a look here. Position. So position it says here is the location of an object with respect to a reference point. What's a reference point? Well, we'll get to that, but it is a vector, so you can circle that part of your notes there. And the units are in meters and kilometers, just like distance. And the symbol for position is D with an arrow on top. Oh, almost knocked them down again. Now, reference point, that's the part we need to know. What is a reference point? Well, the reference point is an agreed upon measuring location. It's a reference. It's the thing that everybody uses. So, for example, all of the students might declare that the school is a reference point, so everything is measured from the school, right? So if the school compared to the 7-Eleven down the street, you'd say, okay, so how far is that? How far is the bubble tea, Pandal bubble tea from the school? How far is the park from the school? Everything measured to the school. So the school works as a reference point. That's all it means. Now, there are lots of reference points, and everyone uses a different one. What we count as a reference point really depends on the situation at hand. For example, astronomers who study space tend to use the Earth as a reference point because, fun fact, most astronomers are on Earth. At least most human ones. Maybe one of you is a space alien coming to visit. I don't know. You haven't told me. So, reference point is determined by the people doing the measurement. And what they set the reference point to, they kind of have to tell you. If they don't, well, that's one of the ways that they can mislead you. Now, it says here further in our notes that the reference point can be anywhere on a particular number line or in space. But we have to agree. Generally speaking, most of the time, we'll set 0 as the reference point because it makes the math really simple, as you're going to see later. But we don't have to. We could really make anything the reference point. It's kind of up to us. So in the example that we've got here in the notes, we've got ourselves a number line. That number line is going to go from -3 to +3. So I'm going to erase some of this information here so we get enough space. I'm really missing having the whole board. So when we write out the number line, okay, so we're going to have +3 and -3. And we're going to put 0 in the middle. So there's 1, there's 2, -1, -2. Okay. So it says here our reference point is going to be 0. Now it actually uses the word origin, which means that's where we're starting. So in this case, our reference point, our origin, is going to be 0. Well, let's figure it out. We're starting at 0, okay? So I take my little thing and I mark here, and this is going to be our initial position. Notice the way that we did that, right? So D arrow, okay, the arrow means that it's a vector. D arrow means position, and I put a little I at the bottom. We saw this with time, right? With time, we were dealing with TF and TI, T final, T initial. Same thing here. Physicists have a certain amount of consistency they like to use. They tend to focus on going with the same basic structure when it comes to naming things, mostly because it makes things easier for them. So then it says that we're going to move to positive. Now, hopefully you guys know positive and negative. It looks like I don't, because I put negative over there and positive here, and that's not usually how this goes. So let's just fix it up. So we're going to go to positive. So we go 2 steps. 1, 2. So here's where we are. Then it says we're going to go 3 negative. Okay, well, I'm going to use a different color. That way we can see that. We'll go with blue. Blue's a good color. So I'm going to start underneath here to make it a little easier. We're going to go 3 negative. So 1, 2, 3. Right there. Now, there's a few different ways that we could be marking each of these points, but since I'm using colors, I'm hoping you guys can see that. Actually, I don't actually know if anyone's colorblind. I never asked. That's bad of me. I should have done so. Well, either way, the next thing it says is that you should end on a -2. And we did. That's our final position. So the notes end up calling it D1 and D2. We could also call this DI and DF with, of course, an arrow. The arrows are important because if you don't put the arrow, it means something different. So you got to be careful with that. Okay, next one. Origin of 1 plus. Oh, that's going to be a little different. All right, so we're going to draw another number line. +3, -3, 0. See, I learned from my mistakes. I put them in the right place. 2, 1, 1, 2. All right, so we're starting at +1, +1. So I begin right here, and I'm going to make that DI. Then what does it tell us to do? It says for us to move -2. Okay, so 2 negative, so 1, 2. So we're right there. Okay, so far so good. Then we'll do the next one in blue again. It says for us to move +3. Okay, 1, 2, 3. So we're ending here. Now, you'll notice, of course, that we're not located at the +3 spot. That's because, of course, we started here, and then we moved 2 spaces, and then we moved 3 back. But since we ended up sort of like 1 space behind 0, we didn't get as far as we could if we had started at 0 directly. So it changes the way things are going to kind of work. Next, it says for us to move -1. Okay, I need another color. I got it out too soon earlier. We'll go with the orange. And it says we're moving -1. Well, that would be from here back 1 space. Huh. That's kind of weird. Our final position is the same as our initial position. I mean, that happens all the time, right? You all, hopefully, got out of bed this morning / afternoon. And I assume that you got out of bed and you wandered off, probably get some food, or maybe to do a bunch of studying of physics. It's possible. And then at the end of the long, long day, which for some of you might be at about, what, 4 a.m., you go back to bed. You start, you leave, get some food, and you wander over to study physics, then you go back to bed. So we actually do that kind of thing all the time, where the starting point and the ending point is the same. That's actually really normal. But it looks weird, especially when we start doing it with math. But that's okay. If you guys take a look at the next several pages, you guys will see that you have a whole bunch of practice that you can do here. Just some number line stuff, nothing that you don't already know how to do, at least until the bottom of the page. I'm not going to go into too much detail on that. There is some practice. It's actually a little bit further in the book. But right now, I want to talk about displacement, because displacement is way more interesting than position. Displacement we can actually make use of. Position, I mean, it's good. Don't get me wrong, but displacement is where it's at. So I will leave you to work on the stuff at the bottom of the page there, and that's page 10. And then right now, I'm going to start talking about page 11. So here we go. So first things first, displacement, you'll notice, is a very similar name to distance. I mean, it's got a D in it, and okay, it's basically all it's got in common. But that's important, because displacement is connected to distance in a lot of ways. So first things first, we've got our word displacement. Now, displacement is the change in position. That is the definition. It's the change in position. It's very simple. It's very straightforward. So if you understand what position is, displacement is the change in that. If you understand what position is. I'm going to assume maybe we need a little bit more work on that, since we only just learned about it like seconds ago. But either way, this is going to be another vector. So, circle that on your sheet. And then you've got your units. You've got your units of meters and kilometers, just like before. Now, what does it mean that they use the same units? They're similar. They're related in some way. Remember, though, a vector has direction along with that magnitude, so there's the big difference. This has direction. How are we going to do direction? Well, we'll get to that. Just patience. Now, the symbol for this is a strange one. It's triangle D with an arrow. And we've talked about that triangle before, haven't we? We saw that. We saw that in time. And we're going to continue to see it come up. Now, our notes here say that displacement is a physics word to talk about the movement away from a reference point. Okay, there's reference point coming up again. Put another way, if you traveled to your friend's house and you had to go around a corner and stop at the lights, for example, distance is how far you traveled. So like, every step of the way, every roll of the car tires. Displacement is how far you traveled if you could fly straight to your friend's house. Maybe you instead of having to go around, you went straight there. What do I mean by that? Just a real quick sketch. You're starting here. You've got your house, a little chimney and a window. Apparently your house is very skinny. Just work with it. And you're going to go up like this, and then you're going to go around the corner, and here there's going to be a stop sign. And then over here is your friend's house. Let's give him a different house. We'll give him a longer one. Maybe we'll give him a porch of some form. There you go. And now you're feeling jealous because your friend has a better house. But I mean, there's a reason why you went to visit them, right? Because you wanted to be in the cooler place. In this case here, the black lines that I drew. Here, let's do it in color. The blue lines that I'm going to draw right here are distance. The red line is going to be displacement. So displacement is what you do if you just measure directly from start to end. It's, if you could fly, if you could teleport, or whichever method of transport you can actually do that you don't want to let everyone else know you can do. And that's it. That's basically the idea. Distance is all the ground you cover, and displacement is how far away are you from where you started. I don't care that you had to go around the corner. I just care how far are you from where you started. That's why the red line is a straight line from start to end. There's nothing in between. It's just boom. That's kind of it. That's basically what displacement is. Now, there's some equations, obviously, and one of those equations is that triangle part again. So let's erase my wonderful diagram and talk about the math. Now, the equations should look pretty familiar. Remember, we talked about the triangle symbol is the Greek letter. Maybe you remember which one. Some of you maybe. Like maybe 3 of you. Maybe. It's delta. Like the airline or the hotel or the, Greek letter. I asked my friends once, I have some friends who are Greek, if knowing the Greek language made math easier. They said it didn't, because they could never tell if where the question started and the math began, or where the question ended and the math began, I should say. I also just think maybe they didn't really like math very much. So. Anyway, delta has a meaning. It means change in. Now, change in tells us exactly what the math is supposed to do. We've seen this when we were talking about time. You might remember that with time, we had a situation that looked like this. And I talked about the fact that people are going to forget that this is the final minus initial. They're going to flip them around, or they're going to forget where to put the positive and where to put the negative. But delta D, displacement, is the same thing. Again, physicists, they do a lot of work, so if they can get away with being lazy, they go for it. It's just very rare. So in this particular case, change in position means position final minus position initial. And that's it. That's the formula. And it's sort of one of those weird things where, you know, the formula is kind of told to you in the description of the idea. If you understand what change in position means, it tells you what the equation should look like. Now, you might remember we talked about the fact that ideas in physics can be shown in the form of words. Most of this booklet is filled with words. Pictures, I try to throw a few in. Can't draw, so that makes it harder. Formulas. There's the formula. All of these are actually showing exactly the same thing. There's not like, you know, one of them is the right answer. They're all correct, 100%. They just do it in a different way. And everybody is good at different things. Many physicists are good with math, but you'd be surprised how much physics is done with pictures. I know, you'd say, what, pictures, really? Physicists can't draw. This is true. Computers help with that. But more importantly, when it comes to drawing things, drawing out or mapping out what's going on in a particular physical situation allows you to better get a grasp of the problem. And that's usually the hard part with physics, is figuring out what the problem even is. Once you know, it gets a lot easier. Usually. So, let's fill in some blanks here. Directly underneath the displacement formula box, it talks about how bold D, remember, bold letter means vector as well, right? So that's just another way to do vector instead of the arrow. So bold D is position. And delta means change in position, at least in this case. Students will often ask why it is that math has such weird symbols for everything, and the answer is because mathematicians are lazy, or put another way, efficient, and they want to have ways to explain things that don't require writing out all the words. I could write change in position, or I could write triangle D with an arrow. This and this means exactly the same thing. It's just that one of them takes only two characters, and well, two characters and an arrow, and the other one takes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 characters if you include spaces. If you're having to write something a lot, you're going to take shortcuts. That's why, you know, emojis exist as well, because people take shortcuts. The difference is that when you're learning something in school, or, you know, out of school as you are right now, you're trying to learn the shortcuts that other people have already developed. You may have your own set of shortcuts that you come up with, and that's fine. But part of learning a particular discipline, a particular subject, is learning what came before, so that way you can have a conversation with other people, so that way they understand what you're talking about. I've mentioned before in class, although I don't think I have to you guys yet, but it doesn't matter if you come up with the cure for cancer if you can't tell anybody, because then nobody can get it, right? And if you've cured cancer but nobody can have the treatment, have you really cured cancer? Bit of philosophical question there for you, I guess. Anyway, moving on, it says here that any change in is a quantity found by a final value minus initial value, which we already said, right? Final minus initial, there it is in blue and red for T and D. And it's the same thing, because it's the same for both of them. Do you remember what change in time is? It's got a name. You could look back, you could check. You could. But there's only so long I can delay, right? So it's an interval of time. as opposed to an instant of time. An instant of time being one reading of the clock, an interval of time being two readings of the clock that you then compare. A couple students have asked me before, is there an interval of position, right, to use the same language? And I guess technically you could call displacement the interval of position, but I guess physicists decided that sounded too silly, so they came up with its own word, displacement. But, you know, there you got it. Anyway, there are multiple ways that we can write the expression. It all means the same things. You can see it there. You can do 2 minus 1. That just means like second minus first, final minus initial. So now we've got an example. A toy car moves across the table in a straight line. A number of lines is marked on the table, and the initial position of the car is -1. The car stops at +3. What is the displacement of the car? Okay. Once again, this is obviously filled in your notes. I'm going to do it again because, you know, obviously I like physics. Here I am sitting here doing physics videos because I like it so much and because I want you guys to learn. And when it comes to doing this, I also want to remind you guys to organize your thoughts. Make sure you organize because it is so easy to just start throwing numbers at the paper, and if you don't keep track of what goes where and what's going on, it's easy to get confused. We've already got a couple more formulas now, right? We've got time formulas, we got distance formulas, now we're getting, and we have speed formulas, and now we're getting displacement formulas. That's 4 formulas already. It's only going to get worse, unfortunately. So if you don't keep organized, you're going to get lost, and if you get lost, you're going to get frustrated, you're going to make mistakes that you really shouldn't make, and nobody wants that. We want you guys to do amazing. Now, let's set up our question. First things first, we've got the given, right? This is the information that's in the paragraph that we want to work with. And one of the things that we see when it comes to any kind of word problem or physics problem is that the more times you have to look back in the paragraph, the more chances you're going to mess up something. You're just going to, like, you know, think one number means something else or whatever. I don't know how many times with grade 11s I've seen where they're like, time, 20 meters. And you sort of look at them and they look at you and then they go, oh, meters aren't time, meters are distance. Oops. And it's just because they're in a hurry, right? They're not thinking things through because they're in a bit of a rush. So we read through the question. It says here, a toy car moves across a table in a straight line. And it says here, the car starts at -1. All right, so our initial position is -1 centimeters. And our final position, it tells us, is +3. Notice these are positions. They're not displacement. We're doing calculations to get displacement. Right now we've just found position. That's all. So we take a look. We've got our given. Next we do our formula. Oh, remember the glory days where we only had 1 formula. Now we've got 4. Did we say 4 or did we say 5? I can't even remember. See, that's how many formulas we have. I don't remember how many we have. So delta D equals dF minus di. Don't forget your arrows. You do need them. They do tell you important things, right? This tells you it's a vector. After we've got that, we're then going to do the calculation. So we put the numbers in the formula. And some people are going to look at this and go, why can't I do all that at the start? And again, the answer is it helps you to keep organized. So we've got ourselves formula, then we're going to do calculation. And then finally, we're going to have the answer. So we start putting in some numbers in the calculation. Make sure you put it in the right order. This is one of the nice things about writing it out. It's labeled. So delta D, that's what we're looking for, we don't know what it is equal to dF. So I'm looking for dF, and I find it over here, it's +3. Then minus, that's part of the formula, and then I look for di, and it's -1. I can put that in brackets if I want to make it a little clearer. Now hopefully you guys remember how it works. If I'm going to subtract a negative number, it's basically the same as if I added them. So I look at this, I do the calculation, and I get a final answer of +4 centimeters. There you go. But wait, some, maybe one of you, maybe. But wait, one of you might be saying, I thought, Mr. C, that you said that displacement was a vector and vector has a direction. Weren't we going to do directions at some point? Like, I don't know which way this thing's going. It's true. And this is one of those weird things that physicists do, because yeah, we should do a direction. Now, normally, if we were to draw a real quick sketch of a number line here, because we're going to do a lot of those, as you may have noticed. Let's see, we started ourselves at -1, so I'll just make this -1. Here's 0. 1, 2, 3. Here's +3. I don't need the rest of this number line. So we started here, and then we moved 4 steps. All right, story checks out. And if I ask you the direction that we moved, well, you'll notice that I first put the dot here, and then I went this way. So I could say 4 centimeters, because that was the units, comma, right. There's my direction. I went right. Now, here's the thing. Physicists are kind of lazy when they can get away with it. And yeah, we could say this is 4 right, and that's not, wrong by any stretch of the imagination. But what happens if I decided to draw my number line in a different way? Or what happens if I were to take this particular number line and turn it so that way it was facing this way? So that way the positive was going towards the board and the negative was going towards you guys. Well, would I say right then? I mean, compared to you, it wouldn't look like it went right. It looked like it would go, away from you. So physicists realized that was a bit of a problem, and so instead of talking about right and left, what they usually do is, talk about positive and negative. +4. Why +4? Because it's positive. It moves in the positive direction. Doesn't matter how I draw my line, I will always move from negative to positive for this particular question. So I could write it as 4 centimeters right. I could also write it as +4 centimeters. And +4 centimeters would be just as accurate. It would give us the same information. Seems kind of weird, because we're used to positive and negative meaning special things. We're used to math class, right? We're used to negative means subtract, and positive means add. Well, they don't. In physics, positive means right, and negative means left. Or sometimes positive means up, and negative means down. Or positive means forward, and negative means backward. And if you think about it, that probably sounds familiar, right? Throw your car in reverse. Reverse. That's the opposite of forward. It's negative. It's backwards. So a lot of these things are not that unsurprising. They're just a little bit different. Anyway, at this point, if you guys take a look at the next several pages, you guys have got loads of practice, okay? So take a look at it. I want you guys to give it a try. You guys have got stuff to do on page 12, 13, 14, 15, 16, and then 17, right? So 17, page 17 is this one here. Maybe you can see it. Once you get to that page, you are basically done practicing displacement. Now, there's a few little unusual tricks in here. I have posted answers online. You can find them in the drive. After that, though, we are ready for velocity. I'll probably make that video right away, but I'll break these two up, so I'll see you guys a little bit later. Hopefully things are going well, you're staying safe, and you are having a good time learning some physics, along with a good time with your friends. Cheers.